Welcome back to JN Lectures. Today we are going to cover the second subunit of grade 9 physics, addition and subtraction of vectors. Now before we get into the actual addition and subtraction of vectors, we have to go over some key terms. Our first term is a resultant vector. A resultant vector, like in the name, simply means the result, or after we do our addition and subtraction or any manipulation of the vector, the result we have in the end is what we call our resultant. To give an example, let's say I have one vector here, and I add it to another vector here, and I have my result. And this result is called a resultant. Simple as that. Next we have collinear vectors. Collinear is just a fancy way of saying parallel vectors, and parallel is just a way of saying that these two vectors are 180 degrees from each other, okay? Which means that if you continuously draw the lines, these two vectors will never cross each other, okay? Now if I were to draw this, I'll attempt to draw them. Parallel vectors, let's say like so. We have one vector here, we have another vector here. I'm trying to draw it so that these two vectors appear to never cross each other or to be 180 degrees from each other. Next we have negative vectors. Now I need to understand parallel vectors before we understand negative vectors, because negative vectors are in fact parallel vectors in opposite direction with the exact same magnitude. Okay, so two things you have to consider. Again, it's a vector, so you have to consider the magnitude and direction. The two vectors have the same magnitude but opposite direction. How do you draw this simply? Again, we use an arrow, the best way to describe a vector. Now the arrow, let's have our one vector here. The other vector is parallel, first of all, same magnitude, second of all. Okay, so they're the same length. And third of all, they're in opposite direction. How do you describe the opposite direction? Simply put the arrowhead on the other side. Simple as that. So these two vectors are negative vectors. Next we have coplanar vectors. Now coplanar simply means on the same plane. These are the only types of vectors we're going to be focusing on this grade unit, because non-coplanar vectors mean vectors in 3 dimensions, and we don't really have to consider that. Next we have position vectors. In order to describe position vectors, let's use a Cartesian coordinate system. So we have our system right here. We have the x-axis and we have the y-axis, right? Now, a position vector simply means you know initial point, you know the initial point, you keep a standard or a solid initial point, and you define the vector by its final point. Let's say the initial point of this vector is the origin, and we'll call that point 0, 0, and we have the vector going this way. Let's say we have another vector going this way. Now to define this vector A and to define this vector B, we don't really have to consider the initial point because we've kept it a standard initial point at the origin. So we just have to define the final point. So we can say this point is 2, 3, for example, and we can say the point for B is -2, -3, right? So a position vector is a vector that represents the position of an object in relation to another point. So this position of vector A in relation to the origin. All right, next we have the actual addition and subtraction of vectors. Now, first let's consider two types of vectors, parallel vectors and perpendicular vectors. Once we cover these two, it's much easier to calculate any other kinds of addition and subtraction of vectors. Now, again, parallel vectors, or another name, collinear vectors, that's right. Parallel vectors are vectors that are not necessarily in the same direction, but they must be 180 degrees from each other. They can be in the same direction, they can be in opposite directions. Perpendicular vectors are two vectors that are 90 degrees from each other. How you represent this graphically is by putting this little box between the two vectors. So this box right here represents 90 degrees. Now, adding and subtracting parallel vectors and perpendicular vectors are kind of different things, so we're going to look through each separately. Okay, finding the resultant of a parallel vector. Now, when you're finding the resultant of the parallel vector, you have to consider something. Are the two vectors in the same direction, or are they in opposite direction? If the two parallel vectors are in the same direction, you simply add the values. That's it. You add the values to find the resultant. If the two parallel vectors are in opposite direction, you subtract the values from each other to find the resultant. To draw this graphically, the two parallel vectors in the same direction would mean that you have vector A here plus vector B here. You see, they're in the same direction because they have the arrowhead is in the same direction. Yeah, if the arrowhead is pointed on the same side of the arrow, it's in the same direction. Now I have two opposite vectors, that means they are in opposite direction. I still use the plus sign because I'm technically still adding them together, but they're in opposite directions. So you would have to subtract these two values in order to find the resultant. So let's give some examples to understand this concept a little better. Now, let's start with two vectors in the same direction. Let's have one vector here parallel vectors and another vector here, okay? You can see I'm making the second one a little longer, so let's call the first one 3 Newton and the second one 7 Newton. I'm using Newton because Newton is the unit of force, and force is definitely a vector. To find the resultant of this, or to add these two vectors, to find the resultant of this, would require us to first decide, are these two vectors parallel? Yes, they're parallel. They don't look parallel, but they are parallel. Are these two vectors in the same direction? Yes. So all we have to do is add the values. The resultant vector, a much longer vector because we're adding two vectors together, would simply be 3 plus 7, 10 Newton. And that's it. We have found our first resultant vector. Now, let us use the same vectors. Let's use the same vectors, 3 and 7 Newton. But let's put these parallel vectors with opposite directions. So the top is still 3 Newton, the bottom is still 7 Newton. Now, we have to first see, are these two vectors parallel? Yes, they're parallel. Are these two vectors in the same direction? No, they are in opposite direction. Therefore, you have to subtract the values, okay? You can do 3 minus 7, you can do 7 minus 3, but just consider the direction. That's the important part. To make matters easier, always subtract the larger vector from the smaller vector, okay? So let me instead subtract 7 from 3. I get 4 Newton. What is my direction? Always use the direction of the larger number, okay? 7 is the larger number, I'm going to put it in the same direction as 7, okay? A little more trickier than adding vectors, but subtracting vectors, the simplest thing to do is subtract the larger from the smaller, no, subtract the smaller from the larger, and then take the direction of the larger vector. Next, we have perpendicular vectors. Now, in order to add and subtract perpendicular vectors, you have to really think of two things separately: finding the magnitude of the resultant and finding the direction of the resultant. Let's start with finding the magnitude of the resultant. You have to use something called the Pythagoras theorem. To find the direction of the direction of the vector, you have to use the trigonometric relations. So we're going to look at each of these separately in case you need to refresh some of your mathematics theorems. Now, starting with the magnitude, we are going to use the Pythagoras theorem. So the Pythagoras theorem, as you can see here, is c squared is equal to a squared plus b squared, okay? Now, if you remember, what this means is you have a and b, two sides of a right angle triangle, and you want to find the third side, or the hypotenuse, c. So let's say we have vector A and we have vector B. These two vectors are at right angles these two vectors are at a right angle to each other, and we can show this by putting this little square right here to represent 90 degrees. Take note of how I drew these two vectors. These vectors are definitely perpendicular, and you can see that I drew them in a head-to-tail, what we call a head-to-tail relationship. This is the best way to graphically represent perpendicular vectors when you're trying to add them. Now, again, let's consider A and B, the two sides that we know of a right angle triangle. In order to find the third side, vector C, we close off this right angle triangle with the hypotenuse. So this hypotenuse then becomes C, right? So our goal is to find the magnitude of C and the direction of C. But now, to find the magnitude of C, we simply use the Pythagoras theorem. So let's first give values to A and B. Let's say A, which looks a little longer, let's give it a 4 Newton value, and let's give B 3 Newton value. Now, in order to find the magnitude of vector C, we simply use the Pythagoras theorem. C squared is equal to A squared plus B squared, correct? We know A and B, so C squared is equal to 4 Newton squared plus 3 Newton squared, right? So C squared is equal to 16 Newton squared plus 9 Newton squared. C squared is equal to 25 Newton squared. In order to get rid of the squared, we can square root both sides, and we get the final answer, C is equal to 5 Newton. And voila, we found the magnitude of C, which is our resultant vector. Next, we have to find the direction of the perpendicular vector. Luckily enough, you simply again draw the exact same graphical representation that you had last time. So we have A and B, and now we actually know the value of C. We know the value of C, right? So we can write this down. We know that C, we found the value to be 5 Newton. We know that B has a value of 3 Newton, and we know that A has a value of 4 Newton. Now, we have all the magnitudes down, we have all the values down. We need to now find the direction. To find the direction, we use what we call the trigonometric I can't even pronounce that properly, trigonometric. We have sine, cos, and tan theta. Honestly, you can use any of these three to find the value of the direction of the resultant vector. Think back when we tried to graphically represent the direction of a vector. We have to have a reference line, correct? And we have to find the angle at which the resultant vector is elevated from the reference line. Now I can see right off the bat, let me use vector A as my reference line, or like a continuous line from vector A as my reference line. Then this angle right here, that becomes the direction of vector C, because we see how much C is elevated from this A. So let's call this theta. You see how I define the angle that I'm looking for. I can use any angle from here, but I'm saying I want to use this angle theta. So if you want to describe the direction, you choose the angle and you choose the reference line. But this is the most standard thing to do. Take the horizontal axis and see how elevated the vector is from this horizontal axis. Now, how do I find theta? Literally use any of them. Use sine, use cos, use tan. But the most appropriate one to use is tan theta. Why? Well, because when you use tan theta, you're using values already given in the question. I'll explain that in a bit. When you use tan theta, you're using opposite over adjacent, right? And you can see here, opposite is B and adjacent is A. You see, I'm not using the magnitude of C. Why? Well, what if I miscalculated the magnitude of C in the previous question? If I miscalculated that, then I'll definitely get both the magnitude and the direction wrong. So it's best to use tan theta. Now, tan theta, you can see it's opposite over adjacent. We see the opposite side, or the opposite side of the angle is B, which would be 3 Newton. And the adjacent side of the angle is A, which would be 4 Newton. So theta would simply be the tan inverse of 3 over 4, or the tan inverse of 0.75. If you have a calculator, which I doubt you will on your exams, you can just punch these numbers into the calculator and you'll find the actual angle in degree form. But this is also okay. This is also a perfect representation of the direction of a perpendicular vector. All right, that is the end of subunit part 1. We still have part 2 next. So I hope you understand the addition and subtraction of parallel and perpendicular vectors.